Yeah, so this workshop, the content you will see was inspired from content developed from John Urbanek and Michael Klein. If you know OpenMP, you will quickly know Michael Klein as well, John Urbanek likewise. Anyway, also for the software that I use, Beamer in this case, which allows me to produce this slide. And when it comes to licenses, what this means is more or less you can do anything you want with these slides except making use of making commercial use of it, or changing somehow something in it and making it look like I endorse what you put in. Apart from this, we're good to go. This short note is just to indicate these slides are designed for live presentations, so there are little text and explanations. So you won't be able, you have all the slides, I believe, by now. So you can all refer to the slides directly in case it is not visible from here, because I know that through the webcam, you can't really see much. So you have your slide in. Like this morning, what they call the moment of truth, which is login on the AWS node, using the username from the spreadsheet, the password from the spreadsheet. If it doesn't work, say it straight away so we can fix it. It's fine, but the earlier we know with the other, fix it. And then if it does work, you can clone the repository whose link is just underneath. Be careful if you copy and paste, which is what I would do. The line break is likely to result in a space in the URL. So you will have to remove that space when you paste it. Apart from this, no other edits here. You will see the repository is made of multiple folders numbered. Each folder represents an exercise, which will illustrate a very specific technique in a simple scenario so that you can learn and practice techniques in turn in isolation. So you can go straight away to the repository you've just cloned. Okay. If you were here this morning, it's exactly the same approach. We have a simple example called preamble. You will see that the codes, the source codes, the exercises, are available in C and Fortran. So pick your pick. So you go to the repository, the language you want, and then the preamble, issue the make, and then run the program. And normally you should see that it will print 4 GPUs. There's been no filter, so 4 GPUs. And when you see this, again, a quick thumbs up, or in the room, it's just a yes or something, because once that happens, we know we're good to go. So we're going to go through a few concepts today. And before we get into anything technical, first we're going to see why we're even going to talk about all that in the first place. Beginning with what GPUs are. So in case you're not familiar with GPUs, don't worry. In this workshop, it's an introduction workshop, so we're going to take it very gentle. What are GPUs? So you may know that this stands for graphics processing units. And you will be very surprised to hear that these are devices specialized in graphics processing. So far, so good. You can see their suitability to application where you have many points. So typically, if you think of graphics, video games, video editing, CGIs, all this, we deal with images, so many pixels on which we typically need to apply the same operation. This is where GPUs shine, really. Because without getting into a lot of details, the GPU architecture is really designed to handle this very efficiently. I derived a simple example of try to imagine you're currently developing an image editing software, and you're trying to create a filter that will darken the image by, say, 20%. And you want, you want to apply this operation to every single pixel, okay? So let's take a very simple picture of what, 6 by 6 pixels, so very, very small picture. CPUs, the way we write applications normally is classic, I should say, with CPUs is we will go through the pixels and darken them one by one. Okay? GPUs work differently. GPUs work with entire subsections of it. And then they can apply the operation to this entire subsection in one cycle. Okay, so the time it took the CPU to do it on one pixel, the GPU can do it on the entire subsection it works on. Then you can go to the next subsection and do that in one cycle as well. Same for all the other ones. That's how GPUs have become really a thing in computer science, because they really managed to efficiently handle this entire set of tasks that we now refer to as graphics processing. I'm going to show you a video. You can also go watch it yourself directly if you want to access the link directly. Otherwise, I'll launch it here. It's a video I really like. You see, let's play. Let's put a video like that anyway. You won't have the sound, but you can still see how CPUs work, basically. You see, they throw little bullets of paint one at a time. When we make CPUs faster, because of course it's not the one I share. Okay. So yeah, here. So you can see, yes, that CPUs work by doing one action at a time, and we can make them faster. With technology, we manage to make them faster and faster. However, GPUs don't work this way. GPUs work by being massive cannons with many, many barrels. However, all these barrels can only work in a very restrained and constrained way. You see, they have no flexibility. They are all parallel to each other. They are all to the same distance from each other, and they can all do only the very same action at the very same time. That's many restrictions at once. But when this is fine with what you're trying to achieve, then it's okay. So now they are going to do the countdown. So let's try to read on their lips. Because, well, for that I need to see lips. Well, okay. That's it. There's the slow-mo if you missed it.
Oh, it's better.
So that's how GPUs work. That's why we call them high throughput devices, because they can really fit all these bolts of paint at once. So it's really a very powerful way to do that, and where effectively you end up having a very interesting device at your disposal, but which has to be used in this very specific environment of we try to do the same operation again and again and again. Let me get back in there, and then we're good to okay. So on the AWS nodes you have, there are 4 V100. To give you an idea, the cores you have on that GPU are 1.3 gigahertz, and you may be thinking, well, my own laptop has 2, 3, 4 gigahertz cores, and on these super expensive GPU, they're only 1.3 gigahertz. Yes, but the reason is on your laptop you have 4 or 8 or 16 cores tops. This GPU has 5,000. So it's 5,000 barrels if you want. To give you also an idea of the bandwidth you can achieve inside this GPU, it's approximately 1 terabyte a second. So things in there go fast. And they go fast without taking much energy. 300 watts. Not thousands of watts, 300. And something I like there is on each of the AWS nodes you have, there are 4 such GPUs. So that means you have 20,000 GPU cores on top of the actual CPU. So now if you look quickly at a comparison, the GPU you have can do roughly 16 teraflops, which is ridiculous. And all this with just 300 watts. If you compare that with 20 years ago, you'll be surprised. So they can do more. They don't take a lot of energy. And if we compare, they're even cheaper because the CPU that you have, I think, is 60 pounds. No, not 60 pounds. Yeah, 60 pounds, yeah. I was surprised to see that the CPU on the AWS node was just 60 pounds nowadays. I think I made a mistake somewhere, but that's what I found online. So I'm still very suspicious from this one. But anyway, the GPU is 4,000 pounds Oh, sorry, but in pounds. Anyways, you can see that the price per core is lower on the GPU. So GPUs are more powerful while using less energy and being cheaper. So we don't even use CPUs anymore because of the limitations of GPUs. Memory transfers. Hey, but you just said that you have 900 gigabytes a second. Yes, inside the GPU. But the GPU has its own memory space. The CPU, the host, has its own memory space. And if you want the two to communicate, you need to use the PCI in between, which has 2 gigabyte balance. And this you go times 8. Number two, remember when I said all the barrels had to do the very same action. So in this case, they all spit a ball of paint. We cannot have one barrel spitting a ball of paint and the other barrel unfolding some message, like in cartoons. They all have to do the very, very same action. If it's not the case, you have to pick. You say, okay, this time it's all the one that spit a ball of paint. The barrels that don't have a ball of paint do nothing. So you may have 70% of your GPU not doing anything because they have to wait for the next cycle where it's, okay, this time it's all the barrels that have a little message to unfold and do, and the ones that had a ball of paint now do nothing. So the GPU performance can quickly get even worse than CPU if it doesn't use it properly. Long story short, without getting too much detail on this, the complexity of the operations you can issue the GPU is more restricted than with CPUs. CPUs are able to do very complex instructions, and GPUs not so much. And from thing called non-coalesced memory accesses, I love this one, but it's definitely outside the scope of this workshop. But it was just that you heard this word once. Coalesced memory accesses, which is where cores load memory locations that are contiguous. So consecutive cores load memory locations are contiguous so that we can do one big memory load. Anyway. Still, GPUs are very attractive in scientific computing, especially. And now with AI, the discussion is over. GPUs are going to be there for quite some time, and HPC as well. It all works through a big pipeline, which I won't go into here. But basically, what happened is we use that for graphics processing. Okay, so we have a pipeline of this stage of the pipeline on GPU does this kind of operation, and this one does this kind of operation, and so on and so on. And we thought, oh, if we could manually control the pipeline, then we could put arbitrary code in there, and we could put like some scientific computation. Even if it was meant to process the graphics, we can basically hijack the GPU to make it do computations for black hole collision. And that's how we got what's called GPU, general purpose graphics processing units. You may have heard of CUDA. CUDA is the NVIDIA solution for this. And the reason it's so popular is because they were, I think, the first one to do it. And they had a great documentation, which is something we rarely see. So when everybody was trying to learn how to use GPUs, they all found the tutorials from CUDA and went straight to it. And it put CUDA in a very strange position for many years. OpenACC was another version, another solution, but much more limited. And we also have OpenMP. There's one now that has become much more popular as well, which is HIP, which is the AMD version of CUDA, if you want. So CUDA is restricted to NVIDIA GPUs. HIP tries to be the more open standard for it. Be that as it may, OpenMP, until recently, was not really a viable solution for GPUs. The support was not really good. But NVIDIA recently improved the support for OpenMP to the point where it is viable now to use it for GPU programming, which is very convenient because we can learn OpenMP for CPUs, do that in a workshop in the morning, and in the afternoon, we can go straight with the same technology on GPUs as well. That's exactly what we're going to do. And we are going to do that later. Anyway, we're going to see something called offloading, that's where it all starts. The reason is we're going to deal with a fundamental split between what we call host and device. The host is where the OpenMP program begins. So typically the CPU. The device is where you may offload computation to, in this case, the GPU. Okay? How to do that? To the people who were here this morning, you know in OpenMP we like single word solutions. We're not going to change that. Target, done. The target construct allows you to transfer the control to the device we're talking about. What we mean by transfer is it's something that is sequential and synchronous. So it means when you transfer some computation to the GPU, you are going, by default, to wait for all these computations to finish before it comes back to the CPU and you can resume execution. We'll see at the end how to do this in an asynchronous way and so on, but for the time being, we're going to learn step by step, so synchronous. And you can combine this with everything we've seen this morning. And we are going to combine this with things we've seen this morning. That is more limited as always, but in theory, everything is possible for the combination. So let's have an example. You have some blocks on the host. Then, if you want to offload, for example, the block B, so the one in the middle, to the device, all you need to do in C at the top, in Fortran at the bottom, all you need to do is to wrap your block around a target construct. So if you were here this morning, you see that it's exactly the same notation. In C, pragma OMP target with the curly brackets, and in Fortran, exclamation mark dollar OMP target and the corresponding closing end target. Okay, so it's really a very light structure, but this takes care of all the offloading for you, and whatever we put in block B will be executed on the GPU. Easy, right? You may think at some point, yeah, but do we always know where we are? Like, can we know if we're on the host or on the device? As you will create more and more functions, it will sometimes be hard to know where you are again. So this is why there's this tiny function. It's just going to tell you if you are on the initial device. Since the initial device, in this case, the CPU, is known to be the CPU, if it says, yes, you're on the original device, it means CPU. If not, it means device. And this is how you can get it to work. The laser is good. So if you want to check if you're on this host or not, a simple call to this function in an F, and that's all you need. Okay? So now, just with what you've seen so far, we can move to the first exercise where you will actually offload something to the GPU. So you can go into the repository, you will see the folder number 2, the HelloWorld, where the idea will be to put some of these computations on the GPU. As I was doing this morning, typically I will give 5 minutes so you can do it on your own. And after 5 minutes, I will go with you through live coding step by step to see how we can do it. Okay? So I'll give you 5 minutes and then I'll come for more help. Yeah, just put a target here. And then so yes, everything I've done here was just to put this target here. Okay. And
Henry's getting an error.
again, no, because you don't need to run the submit steps, just run the program. So just run.
So just take out the submit slurm
Yes.
pieces.
I think I'm going to show, actually, I'm going to do it myself. So I have it here. So I compile it. And then to run it, I just type /bin HelloWorld, and it will run it. Make sense? Okay, perfect. Yeah, it's hard to see any difference, but you have just used your GPU to compile to compute this. It's again, it's
so much easier than I'm sitting.
because that's all you need. To do that in CUDA, you need to write kernels to throw them with thread blocks and to blockading. OpenMP, target, done. That's convenient and attractive. So yeah, you just use your GPU to do something else. So this is one GPU core running. Very good question. Very, very good question. For now, this ran using one core of the GPU. By the time we finish this workshop, you will be able to use every single core of every single streaming multiprocessor of your GPU. If you don't know what a streaming multiprocessor is, don't worry, I'll have you covered. This will be explained in the corresponding unit. There was Carl waiting in the lobby, so just invited him.
Okay, yep.
Work to a C folder, perfect. Right, so if it works, that sounds like we can go to the next. To the next topic. So now that we know how to offload something to the GPUs, we can then try to see how to do it more properly. What I mean by this is we're going to talk about data mapping. Why? Because remember that moving data between the host and the device is very costly. Why? Because it's very slow compared to the performance, compared to the bandwidth you have inside the device. Because GPUs are very fast and they can do your computation much faster, yes. But if you spend 5 hours moving the data, if you at the end save an hour and a half on the computation because you have now a much more powerful device than this computation, since you spend 5 hours moving the data, you still lost 3 hours and a half in the process. So we're going to see how to move the data in a slightly better way. First of all, we're going to really understand where the data goes, if it goes to the device, if it comes back, if it does both, and so on. So let's have a look at this example. Again, C at the top, Fortran at the bottom. Here we have 3 different calculations in CPU code so far. CPU code. We know, for the people who did it this morning, we know that behind the scenes, this means that everything is declared shared. We've seen that this morning, okay? So this and that are equivalent. By default, all the threads will share the A variable and B array variable. However, on GPUs, this does not mean that A and B somehow are shared. On GPUs, one is first private and the other one is shared. So what this means is, by default, scalars are implicitly mapped as first private. In what it means is, well, let's go through each. So scalars, first private. Static arrays, shared. And tofrom. This part here is very confusing because as soon as you deal with GPUs, you have now to deal with this type of things. Well, we were able to use GPUs with just one word. So at some point, there has to be challenge somewhere. This is where we have it. I'm going to go through an example step by step. Let's take a simple code like this, okay? And at the start, on the host, the array, again, for the online people, feel free to use the slides directly. You will have a much cleaner illustration if you try to look at the screen. We have the array on the host. Both elements are 10 and 20. Then we use the target construct. So we transfer the execution to the GPU. So now we have a target, and we just send to both data, 10 and 20. Now, when we update the first element, when we increment it, the value on the GPU is incremented. So far, so good. When we increment the second element is incremented as well. Very cool. This will make for the version 2.1.1. As I was saying this morning, every time I fix the slide, in the bottom left corner, you can see the version number. And when I make a typo, I fix it and I increment it. So if you find the slides online, you can check which version is the latest. So that's 2.1.0, and once this typo is fixed, we'll have 2.1.1. Anyway, these values then, at the end, we have 11 and 21, so 10 and 20 plus 1 each. And we bring this back to the host. That's how it's done behind the scenes. You didn't have to take care of it. It was done for you automatically, but this is what was done. Now, if we try to have just a scalar on the host, the value is 10, okay? Then we have the target, so we transfer the control to the target, so the GPU in our case. This is where things become more annoying. The GPU receives this variable, okay? But every thread on the GPU will make its own copy of that variable. So it means that the increment is on the local copy, the black copy, not the red one that will be brought back to the CPU. So this is a very sneaky difference in the way GPU handles things, at least in OpenMP first. So it's again not easy, but why? What am I showing with this? It's the exact same point in this morning for CPUs. It's that relying on implicit mapping is a risk. I gave you the example this morning. I'm going to give the same one here. Number one, because it might be different. The default behavior for scalars or arrays might be different. And number two, because the default behavior for something may change. In OpenMP 5, do I give the example? No. OpenMP 4.5, they changed. I think the scalars used to be shared or used to be the same as arrays, and now they're first private. So as I was saying this morning, for the CPU part, never rely on implicit mapping. Always explicitly say what you want, so that if one day the OpenMP language committee changes again the default mapping for something, your program is not impacted.
So question.
Yes.
Is this something like pass by value versus pass by reference?
Yes. You can see it this way. I cannot say yes, strictly speaking, for the pass by reference, because from the GPU, you don't have really a pointer on the CPU. Instead, it's more a virtually yes. You pass by reference or you pass by value. Behind the scenes, it's still memory transfers that happen. It's just that once you're on the GPU, since you have this extra copy that's then disconnected from what will be brought back, it looks like a pass by value compared to what could be seen as pass by reference. But I try to be careful with using these terms here because technically speaking, it's not proper for me to use these words. So instead of using implicit mapping, we can use explicit mapping to then say exactly what we want to use. And for that, one word, map. The map clause, and we're good to go. My only sadness with GPU programming in OpenMP is on the CPU part, as you've seen this morning, there's default none. Once you add default none, you're good because you know that you cannot have implicit mapping. So if you don't know what default none is very quickly, as soon as you say default none, you must explicitly say for each variable how you're going to share it. But on the GPU, there's no such equivalent. Maybe one day, but not yet. So map clauses. It's a clause you add to your target construct, okay, just one word. And then we're going to say the map type and the variable name. So what we mean by this is we have three different map types, to, from, and tofrom for any given variable. We have some more if you want, but we won't see that right. The map to from is a very intuitive one, which is the value of the data before the target is going to be sent to the target, to the device. Okay, so they will have a value that was held in that variable before the target was encountered. And then at the end, once the GPU finished all the computation and put some value in this variable, it will be brought back to the host, to from. Okay? Yes, typically we use these two. Two of Supercomputing. Oh, two now. Okay, perfect. So that was for the to from. Now we have the two. The two just means we're going to move that to the GPU, but not bring it back. Why would we want that? Because sometimes you just need some value of the GPU, but you're not going to do anything with it. It was meant to be a read-only if you want. Or even if you update this variable, you're not interested in the final value back on the host, so you can leave it on the GPU. Why is it interesting to do that? Because you don't pay then, you don't have to wait for the data to come back to the CPU. Once it's done, the GPU is finished, it doesn't bring back the data, so the CPU can get back to whatever it was doing quicker. So that improves your performance. And yes, so you go there with your value, but you come back without it. Which means that the original variable you sent to the GPU, once the GPU code is finished, you have nothing, there's no change that has been applied to this variable. It's left untouched. Okay? So let's see an example. Here we have two scalars that we explicitly map as 2. So both are sent to the GPU. Okay? But here, I modify their value. However, if I do a printf at the end, after the end target in Fortran and after the closing curly bracket in C, if I try to print that value, what should it show to me? For A, what would be the value of A after the target? Online, of course, you're welcome to participate as well, unmute or write in the chat. Any idea?
1, 2, 3.
Sounds far right to me. Why? Because we just passed the value to the GPU and changed it on the GPU, but we don't bring it back to the CPU. So whatever happened on the GPU side only exists on the GPU side. We don't bring it back. So the value of the variable A will be still 1, 2, 3. So we've seen 2 from. We've seen 2. So now we're going to see from. So this one from is the opposite, where the data will be directly located on the GPU with no initialized value, okay, because you're not transferring anything to it. Because typically the GPU will be where the initialization will happen for temporary variable or something, for example. And then you're only interested in the final value, which you will bring back to the CPU. Okay? So we can see the example here. A equals 1, 2, 3. A, before that, was uninitialized. But we don't mind because we were going to initialize on the GPU anyway. However, we now want to bring this value back to the host, the CPU. Since we mapped it as from, it will be automatically brought back for us. This can be useful. But these are just scalars. We can also map arrays using this notation. So you're going to say the variable name, then the array notation, so in Fortran it's parentheses, in C it's square brackets, the starting point, or the index, and then the number of elements. It's not start and end, it's start and number of elements. So we have an array of 10 elements, 10 integers here. Starting from 0, I take 10. Okay? It can be a bit confusing at first, but we can get used to it. Okay, You know how to operate, you know how to map scalars, you know the convention for both, the length of the section, how to cover that. Yes, again, it's always worth repeating this one. You don't pass the start and end indexes. You pass the start index and the length. But now that we know this, we can go to the second exercise, where we'll try to practice all that. Okay. So let's try to do it together. So what did you do, first of all, when you wanted to offload this to the device?
Anyone online, any guesses? Or in the room?
We need to use the target pragma.
Yeah, exactly. Okay. So this is good. So we have all this. Let's try. If I run this now, if I compile, 1 times 10 plus 10 equals 0. Would you have any idea why? And by the way, this is one way to check that you really are on the GPU now. Why? Because if I remove the target, look, it's correct. 1 times 10 plus. So that's one way to check that you're on the GPU in this case, because it's designed so that if you just do this, it becomes incorrect.
Because we're not sending back the result?
Yes, because remember all these, B, result, A, X, they are all scalars, which mean that the GPU is going to work on some copies, but never bring back the values. So what do we need to do now to control how the data is mapped to the GPU? Yes, we need to start adding the map clause with to and from. So is there data that we don't need to send the value of to the GPU? Or do we need the value of A, X, B, and result to be sent to the GPU?
Just what result back.
Oh, but
From result.
which values do we need to send to the GPU, and then which values do we need to bring back from the GPU?
AX, 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 B, B, 2.
So, for example, A, do we need to send the value to the GPU?
Yes.
Yes.
Yes. Okay, so that's at least 2 for A. What about B?
No, B you don't, because B,
Yeah.
you really found out it's you.
Okay,
So we just need that.
so for now, not B for 2. What about X? Do we need the value of X?
Yes.
Okay. What about result? Do we need to send the value to the GPU?
No.
No. Okay. Now let's see what we bring back. A, do we also need to bring the value back?
No.
Okay, so 2 is enough here. B, do we need to bring the value back?
No.
Sure, because here we updated the value.
Oh, yeah.
So yeah, we need to bring this one back. X, do we need to bring the value back? Okay, and result?
Yes.
Yeah.
Okay. So we need to send A, we need to send B. No, we don't need to send B because B is overrated.
Did that just did
There's no two from. I thought that I thought they said have one thing. No, because we want to bring A and we need to bring X. Okay, well, let's try that. That looks correct to me. 1 times 10 plus 20 equals 30. Okay. So you see, it's if I remove that, it becomes incorrect. So it really that part. it really comes down to making sure you don't use implicit mapping because it may really catch you off guard. Especially since, again, not so long ago, this code would have been correct without any of the explicit mapping. But because the default mapping has been changed, now it becomes correct. Just make yourself immune to these kind of bad surprises. Do everything manually, explicitly. Okay, great.